Hello everyone, welcome to Math 153, Statistical Reasoning. Today is July 20th. We are in our second to the last week. We just finished a test over chapters 5, 6, and 7 that was due last night, and students did pretty well. There are no out-and-out total disasters yet from students who have been working hard. Tests are always weird in this class, you know. The most common mistake, I would say, on yesterday's test, and I haven't gone through all of them, of course, but I've gone through a few, is that students are asked to find a confidence interval on a standard deviation, and instead they calculate a confidence interval on a mean. And sometimes students use the z distribution instead of the t distribution. And I mention those to you because the same thing will happen in chapter 8 and 9, and when the test comes for those, you want to be very careful that you're reading the problems, because I know you know how to do it, but you didn't do it. So read the problems carefully, and I'm rooting for you. Okay, so yesterday we did 9.1 and 9.2. So 9.1 was saying, let's find proportions, let's make predictions about proportions using confidence intervals, let's make conclusions, let's draw conclusions about proportions using hypothesis testing of claims. And the difference between chapter 9 and chapter 8 is that in chapter 9 we had two populations, and so we had two samples, and that was a big deal. And then in 9.2 we did the exact same thing with means, and the specific point we made was that these means, these two samples, are independent. They're not related in some way. So let's go on now to 9.3. We'll do means again, but they will be dependent, and we call that matched pairs. And they are a really good example, and I'd like to go over it with you. I don't go over examples very often. So remember that dependent, in the sense that they consist of matched pairs. And so there's some relationship, and I gave you the example of before, after. That's very, very common. Or husbands and wives, right? Those would be pairs. Experimental design. This takes us way, way back to an earlier chapter, and we've talked about Ronald Aylmer Fisher, and almost everything he says about experimental design is what we learn in this class. Not strictly true, because I mentioned back in chapter 7 how Fisher and William Seeley Gossett, right? Student, that was his real name. We don't say it very often, so we don't remember. Anyway, they were very good friends and helped each other a lot. And one of their disagreements was on how experimental design should be done, whether it should be purely random or whether you should try to do a blocked design. So this idea here is a little bit more of the blocked design. And so look at this contrast. Some of you have already taken SAT tests, and a couple, not a lot of you, but might take it again. So the SAT test is a scholastic aptitude test. It was designed by a fellow named Brigham. It's designed by a fellow named Brigham, and we may talk about it the very last week. I usually do this little extra thing because we end up having an extra day, it seems, and I make it optional. Come if you want. I really want you to come, but you wouldn't have to. It's not something you're tested on. It's not something you would have to know for the class. But what the topic is ethics, and how ethics plays into statistics. And so I say it's not something necessary to the class, but I would say ethics is important to your life, right? Yeah, I'm pushing it, I know. But no, that's how I feel. It's like you're a human. Whatever you do has an ethical component. Oh, you're doing statistics? Well, then it has an ethical component. And so I'll bring this up again. It ties in somehow, and you'll be surprised. You won't be surprised. You'll be astonished? No. Dismayed. Flabbergasted. What's the word? I need a thesaurus. You'll be no, not shell-shocked. You'll be really upset. Yeah, you'll be really, really upset. Annoyed. No, I need a stronger word. Angry. Yeah, but it's a sense of righteous anger. Like, anyway, we'll come to it. Furious. No, no, no. Because it's got a flavor to it. It's not just the strength of the anger. It's, oh, indignant. That's what you'll be. You will be indignant. You'll be indignant to learn some of the things I tell you in this ethics extra lecture. Anyway, the SAT course. And what we want to know is, wouldn't it be nice if you could take a course so that you could prepare preparatory course for the SAT and you'd get a better score, because then you could go to Harvard instead of going to Chico State. No, there's nothing wrong with Chico State. Actually, it's a really good school. But it doesn't have the reputation that Harvard does. Well, Kaplan is one of these companies that provides this course, and it costs you a couple $100. And you're thinking, well, I'm a poor student. That's kind of unfair. It is kind of unfair. You notice lately, by the way, that a lot of schools are no longer using SATs because they're realizing, wait, maybe this isn't fair. And there's something to that. See, I told you it ties into ethics. More than you know. So there are two ways you could set it up. One is you find a bunch of students who did not have the SAT preparatory course and see what their SAT scores were and find the mean. And then another population, these are students who have taken the SAT preparatory course and see their SAT scores and find the mean. And you have two different populations and they are independent, right? There's no relationship between the two. And you find the means and you compare them. And if the Kaplan students population sample has higher mean, then you say, oh, this seems to be effective. A better way, so here's the better way, use before and after scores. Let someone take the test and then put them through the prep course and then have them take the test again and see how much their scores improved. And before and after, they argue is better. What's the problem with using independent? Well, there might be other things, right? It's randomization. And so you hope everything evens out, but just by luck, one of the groups will have pretty smart kids or pretty rich kids or pretty, more women. I don't know, do women do better on the SAT? Whatever it is, there could be other variables that come into play. And so the advantage of using matched pairs is there's not something else that could affect it. It's the same person. It reduces extraneous variation. This is true, and then it's kind of not. Let me just say that to get a control group, you should have a bunch of students who take the test before and take the test after, except they don't take the prep course. They take the test twice. And how long is it between the group that took it once and then took the prep course and then took it again? Is it a month? Well, then have these other students wait a month. Because I'm thinking, I know this is true. Anyone who takes the test will do better the second time. They just will. And so if you say, oh, the scores went up, yeah, they always do. Wasn't because of the prep course. So there's more thought than Triola here in the book is saying. It's like, but in general, and this bold-faced statement is good, when designing an experiment or planning an observational study, matched pairs is generally better than two independent samples. And that's the big argument that Fisher and Gossett were having. Fisher actually believed two independent random samples was better. And most statisticians nowadays say, no, matched pairs is better. That was the side that Gossett took. My own self, I kind of agree with Fisher. I don't trust him. I don't think people get it right. I think the world is too complicated. There's more variation than people expect. And I know I'm in the minority, but that's just me. Deja vu all over again. Yep. So we learned stuff about chapter 8 and population mean, and didn't we even just do that? Yes. The whole difference here is we're using differences from the matched pairs. So I have a before score and I have an after score. We'll subtract them. How many points did the score go up? It went up 20 points. It went up 30 points. It went up 60 points, whatever it was. I have a husband and a wife and I've measured their IQ and subtract them. And what do you get? You get 8 or -5 or 16 or whatever it is. So we're using these differences. So hypothesis test, we're going to use the differences to test a claim. Okay. Confidence interval, we are going to make a interval estimate of the average of the differences. And so we have a little bit of new notation here. The new notation is that we're going to call the differences D. And D means, suppose you have an IQ test and another IQ test, you subtract them and you get D. Make sure you always subtract them in the same order. Well, yeah, that makes sense. Otherwise, some would be positive and some negative, and they would switch, and it would mess you up. But number 1 minus number 2, say, or do it the other way. Somehow you get a bunch of differences. And then what? Take all those differences and think about it. What are these differences? These are differences from a sample of all the possible pairs of data in the population. So you can think of those sample values. You got a bunch of them, probably more than 30, right? Oh yeah, this is the same stuff, Gary. Hey, cool. I don't have to learn new stuff. And you have all these D's, and you think of the population, which I don't know because I didn't measure everybody, but there is some true mean. And so mu, that means the population mean, sub D, it's the mean of the differences. And you want to, I don't know, tattoo this on your arm or something, emblazon it in your brain. Everything we do in this section is the mean of the differences. And you say, well, what's the difference of the mean? That doesn't do anything for us. It's like, well, I got the first group and I found the average, and the second group and I got the average, and they're different. So it tells us nothing. We are always doing the mean value of the differences. And the exercises will, from time to time, give you this notation and ask you, is this the mean value of the differences, or is it the difference of the means? And it's never differences of the mean. It's always the mean of the differences. I have a whole bunch of differences from my paired data, and I'm finding the average. Except I won't find the average, right? This is what I'm hoping to predict. What I can find is the sample average. So the mean of the differences for the sample. So I got 31 different husband-wife pairs, and I have 31 differences of their IQs, and I averaged that together. And just like X bar is the mean of the X's, so D bar is the mean of the differences, D. You could also take all of those D differences, however many there are, and you could calculate the standard deviation, and the sample would be S sub D. Great. And you're thinking, how about sigma sub D? Well, the reason they don't put it is, well, you don't have any idea what it is. I mean, they're honest about it this time. It's not like, supposing you know it. Well, you know, they know you don't. How many pairs of sample data? Be a little careful with this. Don't say, oh, I have 70 people, so N is 70. No, you have 70 people, and 35 are husbands and 35 are wives. You have 35 pairs, N is 35. I don't think you'll make that mistake, but I mention it because you could. What are the requirements? These are actually matched pairs. It's a different technique. Has to be an SRS. We're used to that. Has to be normal or large enough sample that it doesn't matter. And then you're using a T because you don't know sigma, and you plug this in, except we don't plug it in. We're going to use technology, and it'll give us a p-value. If you have to know critical values because someone is thinking you're old-fashioned and wants to test you on it, then you know to use the T distribution calculator. Degrees of freedom is just what we're used to, n-1. If you're getting a confidence interval, then you calculate the margin of error, and you add it and you subtract it, and you're thinking, this is just like review week. It is kind of, isn't it? This is kind of fun. Gosh, you kids know a lot of stats. And so what do you do? Well, those are the procedures. Make sure that you do have dependent samples, and make sure that they are simple random samples and you have at least 30, and then subtract each one. So for example, before minus after. And I'd already said be consistent. And then you have a whole bunch of D values, find the mean, find the standard deviation, plug the stuff in, and you're good to go. Equivalent methods. Remember, proportions do not always have the same result when you use a confidence interval method. But means and standard deviations and variances do. You can use the hypothesis test, the p-value method, you can use a confidence interval, you can use a critical value method, whatever, they will all get the same result. And this, we've said this before, but I'll mention it again because yesterday I got the feeling a couple students weren't sure of it. The null hypothesis means the mean might be 0. And so how do you know? Well, if it includes 0, if your confidence interval includes 0, then you fail to reject because you're saying, I don't have evidence that it's not 0. It might be 0. And they give you an example. This is one that the exercise is like. This is a really good one. So you have best actresses and you have best actors. These are for the Academy Awards, the Oscars. And these are particular years. And so they're matched pairs. This woman and this man won an Oscar the same year. And you go through and you say, well, subtract them, and 28 minus 62, 28 minus 37, and so on like this. And they got these 5 values. And the argument is made that society is kind of unfair to women, right? You have an old man who's very distinguished, and then you have an old woman and she's extinguished. It's like, no one wants to look at an old woman. We want young women in bikinis. And yeah, that's society. What can you do? And is this true? Well, here are 5 years chosen at random. And you say, don't you need like 30? Well, not if they're normal. And I guess they are. So they've checked this. We should check normality. And so somebody did this. They put it on a dot plot, and they don't see outliers. And the normal quantile plot, it kind of looks straight. And so everything's good. And then they just subtract. We've already done that. Find the average, the mean of these differences. That would be D bar. And then find S sub D, find the standard deviation of those. And you plug everything in. Oh, we should have made a null hypothesis. The null hypothesis is there's not really any difference between the age of men and age of women. It's fair. And the original claim is no, the women are always younger than the men because nobody wants an old woman. Yeah, right. And they get this thing, and anyway, you can read it. You'll know what to do. You'll understand it. If you use technology, yeah, because we're sensible, then you'll get a test statistic and a critical value. It might show it. Ours doesn't. Typically, it tells the test statistic and the p-value. But if we want the critical value, we have to use the t calculator. And our technology will tell us the mean of the differences and the standard deviation of the differences. So they do an example with technology. Nothing tricky about it. And when I say nothing tricky about it, well, what if it's not normal? What if you have a small sample? Well, then you use fancy methods that we don't do in this class. And as I say, we're done. That was pretty quick. Let's work a couple. Oh, gosh. Oh, my gosh. Let's not show everyone's scores to everybody. Man, I got to, oh, that messes me up now. Oh, I shouldn't have done that. Give me a second here. I got to fix this. Oh. This is very bad, Gary. See if you can fix it. Let's see if I can fix it. I can fix it. I can fix it. But it'll take me a minute. Sorry. Yeah, okay. Anyway, I know what I'm doing. Obviously, I don't. Okay, assignments. Let's work a couple. And you'll see how easy these are. You'll notice a slight difference in these, and that is that most of the exercises do ask you to work with raw data instead of summaries. And the reason for that is you kind of can't give a summary. It's easier to give a bunch of pairs. And so, first question, it's a thought question. I'll let you read it. I don't think you'll struggle with it. This is just, can you identify which are matched pairs and which are independent? So that's a good thing to know, because you have to know it's a thinking class, not a math class. You have to know which technique to use. This is that best actor, best actress problem. And they give you the individual data because that's kind of what you need to do to calculate the differences. So open it up in StatCrunch. Yeah, come on, you. Open it up in StatCrunch. We go to Stat. Well, before we do that, let's do things properly. Mu sub d is the mean of the differences. The null hypothesis always says, there's no difference. And so there's going to be a 0 there. And what's the original claim? The original claim is it's in here somewhere. Oh, scroll up a little, Gary. Test the claim that the population of ages has a mean less than 0, meaning the actresses are younger. Okay, so less than. And I hope you saw how I did that, right? The null hypothesis is a claim of no difference. And so there will always be a 0 here. And there will always be an equals here. And there has to be a 0 here because the values always match. And what's the original claim? So these are actually easier than any we've done so far. That's kind of sweet. And once we've done that, here are the data. You go to Stat. You say, what kind of thing are we doing? We're doing something about means. You can see the mu. And you say, means, do I know sigma? No, you don't have any idea what sigma is. Then I'm going to use t. And that's the same process you've gone through before. One sample was chapter 7. 2 samples was section 9.2, independent. For us, we use paired. This is what they call the 9.3 dependent. So these are paired data. Each row is a pair. And so the actresses are one and the actors are the other. And notice they've written this in a slightly different format. Yeah, you're subtracting. And so equals 0 and less than. I'm just making sure that this matches this. That wasn't super difficult. And I have the stuff. Here's a t-stat, negative 2.56. Quite a ways to the left. Not extremely to the left. We'll round it up to 2.57. Identify the p-value, which is pretty small, 0.015. And our alpha was 0.01. And this is just silly. You've heard me complain about this before. Why point? It doesn't matter. But because of that silly value of alpha they've chosen, this is actually bigger. Since the p-value is greater than, if p is high, the null can fail to reject, meaning there isn't sufficient evidence. Someone says, if you look at this, do you see how the actresses are all younger than the actors? And if you wanted to just verify that, let's do that real quick. We're going to go to graph, we're going to go to dot plot, and we'll just plot them both. And you'll see, oh yeah, obviously the actresses are younger than the actors. I mean, look, there's the actresses, there's the actors. Any nincompoop can tell that. But because some nincompoop chose a ridiculous alpha, they say, no, I don't see it. That could be ordinary variation. It's like, what? Seriously? Yeah, these two are outliers. No. I mean, no. You can tell that's kind of normal, that's kind of normal. Yeah. Let's do it with a confidence interval instead, and you'll get exactly the same result. What will the result be? The result will be since we failed to reject that the confidence interval will include 0. So we're expecting this one to be negative and this one to be positive. So we go back up here. We've already set everything up so we can go to options and edit and get a confidence interval. And here we have a one-tailed, less than, one-tailed, so 0.01 on the left has to be symmetric. So you also have 0.01 on the right. We have 0.98. And the left is negative and the right is positive. And again, this is what I said. This is really negative, and this is just past 0. And so any other value of alpha would have noticed, hey, it really does appear as though the actresses are younger. And if that's a problem, that's for society to determine, not me. Then let's do something about it. We'll figure it out together as people who like each other. If I round this to 1 decimal, I get 1.0. Nice work. So is this the same conclusion? Well, it does contain 0. And so we fail to reject. That is the same conclusion. And that's how you work that. Here's another one, same sort of thing. Yes, Christina.
So I have a question. Can you hear me?
Yes.
Okay. On that confidence interval, did you have to take the alpha and then square it because there's 2?
No, I had to. So here's the idea is, here's the idea. We know that I'm using a t. And we're saying, well, when does weird stuff happen? And I say, well, there's a less than. So weird stuff happens over here on the left. And what was my alpha? It was 0.01. And degrees of freedom, I guess we should do that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 9. This is all done automatically for us in the background, right? So we didn't have to worry about it. But there is where weird stuff happens. And the thing is that we know these have to be symmetric. And so I have to have the same amount of 0, 1 over here on the right. And so if I think of it as a between, in order to get the same value, let's look at that value. In order to get negative 2.82, and this is the mistake students make. It's easy. It's an easy mistake to make. You say, well, 0.01, so it's 99 that's left. No, that's not quite as wide as it needs to be, because you have to have a 0, 1 here, and you have to have a 0, 1 here. So it's actually 9.8. Now, okay, that's the 2.828. So I didn't square it, I doubled it. And the way I figured that was I looked at my hypothesis test. I said, this is a one-tailed test, so there's 0.01 alpha over here, but it has to be symmetric. And so if there's 0, 1 here, there has to be 0, 1 here. How much is left? 98. And so when they say do a confidence interval, I say do a 98% confidence interval. Did that clear it up for you, or do you want me to say it again in different words slower? I could do that too.
No, I think I got it. So you don't have to square it like you would for the...
No. That'll come soon enough, because we'll get to 9.4 and we'll have a tool, and we know that our tool is a variance tool, and they will always ask us questions about standard deviations because they're easier to work with. And then yes, we'll have to square them going in and unsquare them coming out. That'll all happen again.
Okay, thank you.
Okay. So these are more, people vote for the tallest candidate. See, this is the proof, or is it? So you'll try it out. I've read that. People always vote for the tall guy. I shouldn't sound so skeptical, because now you know how it's going to turn out. Who talks more, men or women? Well, everybody knows women are chatterbox. And so you look at this and you say, well, more, less, more, less, lots more, lots more, less. It's hard to tell. But you could do this. Don't believe it, right? Because these numbers are made up. This is an interesting one. People hold a strip of paper in their right hand and they let go of it, and anyway, they grab it again. It's released, and then they're supposed to grab it. I think people use this to test the effects of alcohol intoxication too. But here, nobody's drunk. It's just if you're right-handed, you should be faster with your right hand than your left hand. And this is sloping up, and so you think to yourself, yeah, as the right hand goes better, the left hand goes better. But wait, I thought we're trying to see if they're different. Are they different? The original claim is no, there's no difference. Maybe we should do this one. So what is mu sub d? Anybody want to get this one right? I told you they would ask you.
Mean of differences.
Anybody? Yep, it's the mean of the differences. So each of these has a difference, and if you read off, you'd get the values, and you'd get the mean of the differences. Here are the values, right? 123 and 131. Yep, that's the first one. 138, 159, and so on. I'll get it ready, just so that it's ready. We still have to set up the hypothesis. So original claim, no difference. Well, we know that this is always set up to equal 0. See, here they don't even let you put in the 0. They're like, yeah, it has to be 0. You know that now. And what's the opposite of equals? Well, the original was no difference, so there is a difference. And here, this is a weaker test. We'd have to have a pretty extreme difference to detect it. What's the test statistic? So here we go. We go to stat. We go to t. Why are we going to t? Because we're doing something about means and we don't know sigma. These are paired data. It's the same person's left hand and right hand. It's not like a bunch of left hands and a bunch of right hands. And let's see. We'll do it like that. And we want an equals and a not equals. Hey, it's already set up for us. That was sweet. They're really, really, really different. That's way far to the left. 6.595 after they rounded. And what are the critical values? And you're kind of like, wait, I already know the p-value. Why are you making me do this? Well, because some of you, when you're working on your masters, and I really encourage the nurses especially to work on your masters. Yeah, it'll be good for you. You'll learn a lot more. You'll get a lot more interesting positions in the hospital. It's more rewarding. You'll feel better. But in that situation, you'll be taking a course in research methods, and it'll have a little bit of statistics, and 90% of you'll go, oh yeah, Gary taught me this. I know this stuff. But they'll also have you do some things with critical values because you'll be doing old stuff, right? And old stuff typically uses critical value method a little more often. We need the T calculator then. This is a two-tailed test, and we have 0.01. Where's the 0.01? It's on either side. Combined, that would surprise us. And so what's left in the middle is 99. How many hands were there? There were 5 pairs of hands. 5 minus 1 is 4. And so we get these values. Plus or minus, because either side, two-tailed test, 4.604. Okay. What's the conclusion? Well, this is 4.604 on the negative side, and we found a test statistic t-value of -6. This is definitely in the critical region. That means we will reject. There is enough evidence. And read through this carefully because you hate to get it wrong. The original claim was there's a difference. And we say there is enough evidence to warrant a rejection of the claim. We think there is a difference. So we're rejecting a claim. Sorry, let me back up. The original claim was there's not a difference. The null hypothesis is there's no difference. There is no difference. We reject the claim that there's no difference. There is a difference, and we have enough evidence. So that's how to talk yourself through those. I think that's the hardest part of the class, is that stuff right there. This is blood pressure measurements on the right arm and the left arm. Wait, shouldn't they be the same? Yeah, I don't know. Talk to a nurse. They know that better than I do. Hospital admissions from motor vehicle accidents. Because you know Friday the 13th is unlucky. There will be more accidents. And so, well, let's see if there are. And they used the Friday just before because it should be kind of similar, right? But it's not unlucky. That's kind of an interesting one. This is similar using a confidence interval. These are adjacent plots of land. They had corn seed. Remember that Ronald Aylmer Fisher's first job out of college was working for the Rothamsted Agricultural Research Center. And this is exactly the kind of stuff they were doing. So he improved it because when he found the records, they were kind of garbage. This is pain before and after hypnosis. I don't have to go through all these. You know how to do them. They're easy. Yeah, right. And then you get to the thought questions eventually. No, none of these will kill you. Speed dating again. Okay, is there a difference between what the men think of the women and the women think of the men? Oh yeah, there is. Let's not talk about why. Ladies, you know why. It's because the women take more time getting ready. That's a cultural thing. And so the men think they're more attractive. And the women look at the men and think, seriously? Yeah, because men, right? I say that being a member of this species. We are in 4. How about if you have 2 variances or 2 standard deviations? Hey, something new. I lied before. I said there's only one big idea. There's actually 2 big ideas that are new. And that's this thing we have called the F test. And it's named for Ronald Aylmer Fisher. And it uses the F distribution. Yeah, the F test uses the F distribution. Is that like baby stuff? I wonder which distribution the F test uses. Like the F test? Yeah, this is too easy. And you can do hypothesis tests, and you can also do something else. One thing we have to mention here is this test is not robust. It's very sensitive. If your data, and there are 2 samples, right, from 2 populations, if they are not both really, really normal, then don't use this at all. It just won't work. I would say, in fact, that this particular test, this might be the thing that's in the real world, this is rarely done. If it weren't for the fact that there's this beautiful symmetry, look at 7, look at 8, look at 9. Oh, they're exactly the same. And the fact that we can do this so fast, a person could make an intelligent argument about just skip this section. We never have. Nobody ever does. You know, we don't write the test, and so we have to do it. I probably wouldn't skip it because I like the symmetry. The tool, and this is something you're used to, the tool is for variances, but you use the same procedure for standard deviations. Okay, I got it. F-test could be two-tailed, left-tailed, or right-tailed. Oh man, that's complicated. Okay, so here's what we'll do, and this is a tricky bit. The larger of the 2 sample variances, because you have two samples and each has a variance. That's S1. So you say, wait, which is 1 and which is 2? Whichever is bigger is 1. It just is. That means the smaller is S2. Okay, well, that's easy, Gary. Why do you say it's tricky? Because they won't give it to you in that order, and you'll put them in wrong, and you'll get weird stuff for F, and you'll miss the problems. So when you see, wait, I have two populations, two samples, I'm using the F test, make sure that the bigger is number 1. So here we go, hypothesis test. You have two population variances, okay? And S1 is bigger, yep, and S2 is smaller, the other one. And N is how big it is, and sigma, that's what you're trying to predict. Got it. They have to be independent. They just have to be independent. What if it's husbands and wives? Well, then you can't do this. They have to be simple random samples. We're used to that. They have to be normal. What if I have a really big sample? No, they have to be normal. They just have to. So here's the deal. If you look at this, you know that S1 is bigger than S2. So if you have a bigger number on top of a smaller number, in math they call that, right? Remember back to 5th grade or something, it's an improper fraction. Well, what does it mean? It means this is bigger than 1. So F starts at 1. It's always positive. We haven't seen what the F distribution looks like. You're thinking, is it kind of like the chi-squared? It's a lot like the chi-squared. But the chi-squared starts at 0, and this starts at 1. What's the null hypothesis? There's no difference between those variances. You use technology? Well, yeah, show me the formula. Wait, where's the form? They don't even show you the formula. Nope. It's really, really complicated. You're saying, yeah, I mean, this is the formula. Critical values. Yeah, there's complicated stuff because degrees of freedom, right? And so this is why no one will ever ask you to use the table. You have a column and it has its own degree of freedom, and you have a row and it has its own degree of freedom, and it depends on the two sample size, and it's just horribly, it's ugly. So we won't worry about it. We'll just use technology. I'm happy with technology. The only thing you have to remember is S1 is bigger than S2. And do make sure that you verify that it's normal. Exploratory data analysis. What does the F distribution look like? And those of you who've kind of been paying attention, you think, that looks like a chi-squared. It looks a lot like a chi-squared. And if you didn't know, if this wasn't labeled, you'd say, oh, that's a chi-squared. But it isn't. It's not symmetric. It's always right skewed. And this is kind of flat because there aren't any values that are fractions. It starts right at 1 because S1 is always bigger than S2. And so if you divide, you get something at least 1 or bigger. And they mention that it's not symmetric, can't be negative, can't even be less than 1. And it actually depends on 2 different degrees of freedom. Well, what does this mean? Suppose they're equal. There's no difference in the variance. Well, then what's the ratio? Something slightly bigger, because there's always variation. Even if they're equal, the sample, it's a little different. So there's a slightly bigger number over a slightly smaller number. It's very, very close to 1. And what does this mean? There's no difference. Suppose that they're really, really far apart. Oh, there's a huge difference. Well, then S1 squared over S2 squared will be a large number. So a large number means, yeah, there is a difference, reject. Small number means there's not much of a difference, fail to reject. And so this is what they say, large values of F, reject. Do not think that they are equal. That's evidence against. And this is not a phrase they've used, evidence against. They've not said this before. It's kind of new, but you think about what it means the way I explained it. And I think you'll get it. And they ask it, once in a while they ask you this, and you have to think, oh yeah, right. So here they give you an example. And of course, it's a thinking class, not a math class, so you do have to check the requirements, otherwise don't do the stuff. And then they work it out for you. You could use a critical value method, yeah, because we do have a calculator for the F. Okay, great. And so if someone wants to know, you could put all this in. I don't think they actually ever ask you a critical value because it's kind of complicated. I don't remember that they do. But if you feel old-fashioned someday and you just want to get out the tables and try it, you could. So there you go, right? This is an alpha of 0.05, our typical alpha, and it's a two-tailed test, and so they're split. That should look kind of familiar. Usually you'll use technology. Um, I don't know if this is worth mentioning. It's not. Skip it. Alternative methods. So there are these really cool things you can do. And they're kind of cool and we don't do them. Ooh, the Levine-Brown Forsythe test. I got to double check. 9.4. I think I've deleted it, but I've seen in the past where from semester to semester the problems will creep back in. Maybe someone who's already done it. Did you see a thing called the Levine-Brown Forsythe test? Anybody see one of those already?
I haven't.
Okay, good. Was there a problem? No, I think I just deleted it. I don't know. We'll find out, I guess. If you do see one, skip it because I don't expect you to use that. It's not on a test. It's not on a quiz. Usually, yep, here's a thought question. They do have a thought question, so think about it. Okay, here's a good one. This is nice. So was there interbreeding of cultures? And what we have are some skulls, some very, very old skulls and some pretty old skulls. So these skulls are 6,000 years old and these skulls are 2,000 years old. And how much difference is there in their skull sizes? Well, how much difference, the variation, that's going to be standard deviation. And if there's not much variation, then you can think, oh, the men of this tribe and the women of this tribe, they combined. And so this is an interesting thing to physical anthropology. Whether there was interbreeding, these are independent, simple random samples. Good, I'm not on this so far. Simple random samples, normal distributions. Here's the claim. The claim is that the variation in 4000 BC is the same. So if we have the same for our original, our opposite is not the same. We're looking for an equals and a not equals. It looks like that. That was easy. Fantastic. Okay, this is really, really easy to do. What you do is you open up a StatCrunch window. I'll just get a new one. The ones I've been using all day have become kind of cluttered. Spoiler alert, I'm going to do it wrong. We'll see if you catch me. You go to stat and you say this is variance, right? Yep, it's variance. And I need 2 samples and all I have is a summary. You're thinking this really isn't hard. I'm liking this, Gary. And so what do? You put in the variance. It's 5.17, 5.17. Anybody catch me? Yeah, so I got to square it. Okay, so you did catch me, except you didn't. 5.17. I'm going to square it, square it, square it. Hey, there it is. I'm going to use the Control-C copy, and then I'll just paste it in. Nice. And how many were there? There were 30. Wait, are these matched? They're both 30. No, they're not matched. They have to be independent. It's one of the requirements. But I've said before, I'll say it again, you get better results if your sample sizes are close to each other. So again, I put in a 5.32. Nope, can't fool me, although I already have. You're thinking, no, you didn't. We caught you. No, you didn't catch me. Make sure you square it. And then what? I
Well,
want
you
it to be an
spoiled it
equals,
before
and
we
that
could.
equals. Yeah, but I still fooled you. That's what I'm saying, is I still fooled you. It's 0.94. Okay, 0.94. Predictions? It's definitely wrong. You're thinking, well, what? You square. Why is it wrong? What's the one thing I said you have to be careful of when you're doing these?
The bigger one comes first.
Yep. What did I just do?
The
I put the
opposite.
smaller one first. They put it in the wrong order. Hey, Gary, you said that F has to be at least 1. Yeah, this is, I mean, I don't know how, but it would be great if your brain threw up a red flag and said, wait, this can't be right. But it doesn't. Okay, let's fix it. Let's grab this one. I'm going to copy it. I'll cut it. I'm going to cut it and put it in here. And go back to my calculator. I still have the value. I'll copy it and I'll paste it in here. And let's redo it. Oh, that's a lot better. I'm bigger than 1. I'm supposed to be bigger than 1. You want to see that I was wrong? And they're kind of friendly. They'll say, you know, S1 has to be the larger. But a lot of students I know, when these come up, they're like, oh, and they just hit the OK button. Then who actually reads these, right? Right? Talking to you. I don't know who it is, but I've seen them do it. I've seen them do it. 2 decimal places, 1.05. And what did we say? Yeah, because I did the sample ratio. Don't do the sample ratio. Do the F stat. Oh, it rounds to 1.06. Some people never pay attention. That's me. What's the p-value? Well, this is really close to 1. We know that large F values argue against the null hypothesis. This is a pretty small. I don't think we're going to argue against. And no, this is a whopping huge p-value. 0.879. So a p-value that high, we can allow the null to fly. We failed to reject. So it's one of these. And the fail to reject always says insufficient. So someone says, you know, these skull sizes, 131 and 136, have the same amount of variation. And we don't have any ability to argue against that. Have we proven they're the same? No, but we can't prove they're not. And so we'll accept that they're, right? Did you read my little thing? I wrote a thing up in course documents about how to interpret the final results. I really encourage you to read that. Anyway, that's the big deal, is be really, really careful. This one, oh, look what the, oh yeah, this one's all right. It's bigger. Yeah, that's all right. Oh man, there's a bunch of numbers here, and yeah, you have to pull them out. One of the numbers is bigger. 2.10, yep, that better be S1. 0.76, that better be S2. But they're not super hard, and look, there's only 11 of them. It's like, that's hardly any, because you still have several thought questions at the end. Let's do this one just because it's one-tailed, so it'll give us a little variety. So we go to stat. Let's read it, Gary. Don't assume the students know everything. This is the number of words spoken in a day by men and women. Okay. And who talks more? That's a different question, right? Who talks more would be this. Who has more variation in the number of words spoken in a day? And they're arguing, the claim is it's more men. Sometimes men are moody and they just don't say much. And so they have a very low number of words spoken. And sometimes men are all excited, and women, you know, men, and you're thinking, well, yeah, sounds right to me. I don't know if it's right. I made it up. but I like to get a backstory. It makes me feel better about this. We go to variant stats, to sample. We don't have any data. We just have a summary. Which is the bigger one? 8632. Okay, so put in 8632.9. Yeah, I'm seeing if you'll stop me. No, you got to square it. Oh, yeah, you got to square them. Square them going in, unsquare them coming out. Yeah, equals. That was useless, Gary. 8632.9. Don't hit the equals button, Gary. Hit the square button. Oh, that's a huge number. Copy it with a control C and I paste it with a control V. There were 187 men. And over here we have 7301.5. Standard deviation of the women. We square it to get the variance. Control C to copy. Control B to paste. And there were quite a few more women, 211. I kind of don't like that. Oh, by the way, when we did the null and alternative before, what was it? It's more. So I'm looking for an equals and a more. There you go. I didn't point out to you that this is actually different looking, right? I said make sure there's an equal, make sure there's a greater than. Equals, greater than. But what's this one? So here's the deal. If the claim is that sigma 1 squared equals sigma 2 squared, then what is the test statistic? The F value, sigma 1 squared divided by sigma 2 squared. Well, if they're the same, if they equal each other, then you divide something by the same thing, you get 1. And that's why this 1 is here. You will never, ever, ever have to change it. You might have to change this depending on what kind of claim it is. Anyway, once that's all done, it's a matter of rounding. If you're good at rounding, this class is really easy. I'm going to say 1.40. That's what I'm saying. And the p-value is really, really, really small. 0.009. I bet that's smaller than alpha. Alpha is 0.05. It's definitely smaller. So we will reject. There is sufficient evidence. Reject always has sufficient in it. The number spoken in a day by men does vary more. And you say, well, yeah, 8,600, more than 7,300, but it might have been ordinary variation. You don't know. You have to check. This one, yeah, there's nothing hard about this. This is magnets for pain again. And here they're not saying how much pain did it relieve or did it relieve pain. It's just how different was the reaction, right? Does the difference vary more? And that might tell you something about whether it works. It might not. This is a geyser. You know, the most famous geyser in the world is Old Faithful in Yellowstone Park. And I can remember when I was a kid, my grandparents took the family to Yellowstone and we went and saw it. And there was a sign and it said, next eruption, 45 minutes. And then you'd go and sit down and you'd wait. And you'd chat, maybe eat a sandwich, whatever, play with the ground squirrels. But you just wait, and there were lots of benches, and in 45 minutes it would go off, and that's really cool. And then what, in the 80s or so, there was a big earthquake at Yellowstone, and Old Faithful is not quite as faithful. It seems to vary more. And here are some data, how many minutes between that it used to be, and you say, yeah, they're in the 80s, they're in the 90s, there's an outlier, they're like all 80s and 90s. And these are 80s and 70s and hundreds, and do these vary more? I don't know. Let's find out. Let's do this one. We got 2 minutes left. We go to variance stats. This is the friendliest one, the one where you have two samples with data. And why is it friendly? Because if you forget, wait, the big one has to be, they'll fix it for you, right? I don't know which one's bigger and which one's smaller. No, they'll fix it for you. What's the null and alternative? The claim is that the variation has changed, so it's not what it was. Assume they're normal. Yeah, I don't know that the data entirely convinced me of that. Yeah, I can't get there. I was going to do a little graph for you. But this is nice, and you can tell that they did it correctly because, yeah, F is bigger. And what were the actual unadjusted variances? Yeah, let me just show you. Summary stats, they are in columns. We want to know both columns, and we want the, I scrolled right past it. We want the variance. And the recent was the bigger, and so they put that there. Yeah, by luck, we got it right. But I think it fixes it either way. Maybe I'm wrong about that, but I think it fixes it. Anyway, the F stat is 1.75. And the p-value is a pretty big 367. And if it's big, if p is high, the null can fly, fail to reject, which means insufficient. So somebody says, you know, it's not as faithful as it used to be. Then we say, haven't proved it to me. Looks kind of the same. No, they're not the same at all. Look at the difference. Could be ordinary variation. That's lots of variation. Yep. Sometimes ordinary variation is lots of variation. We haven't proven that they're different. And then look how many, several, 4 more thought questions. So this is pretty easy homework. The main thing is, I'll say it again, make sure that S1 is bigger. And watch out for that on the test too, right? Okay, we are out of time. I'm happy if you're happy. Put my face back up, Carl. That finishes chapter 9. We are done with chapter 9. And what comes next? Obviously chapter 10, except it doesn't. For weird reasons, we do things in a slightly different order. Next comes 11.1. We skip 11.2. Then comes 12.1, and we skip the rest of 12. And then we come back to 10. And I will mention just while we are here, give me 1 second, that chapter 10, yeah. Where are you going, Gary? I'm trying to see over I'm trying to open course documents. Why am I opening course documents in that window? Course documents. No. Find the window, Gary. Here you go. Course documents. Carl, share that with them real quick. We got to go. There's course documents. If you scroll all the way to the bottom, you'll notice there are 2 new videos. And one is on 10.1. It's about 36 minutes long. And one is on 10.2. It's about an hour and 10 minutes long, and it's kind of long. You might recognize these words, correlation and regression, as being words that we met in chapter 3. It's like, wait, this is that again? Yep, it's that again. So I typically do not talk about these in class at all because I have nice videos that do what I would do. And so we will do 11.1, we'll do 11.1 and 12.1 tomorrow. Thursday, I'll probably jump into 10.3. I could talk about these very briefly if you wanted me to, but 3 and 4 and 5. 5 is a little tricky because you have to use Excel, and that'll feel new to you, some of you. And I've written up this document showing you how to do it. If you're on a Mac, it doesn't work quite as well. You'll be frustrated a couple times, but you'll get through it. Cool? Cool. I'm happy if you're happy. All righty. I'm a couple minutes over. Let's quit. Thanks, everybody. We will see you tomorrow. We'll be in chapter 11, goodness of fit tests. It's really a chi-square test. Nice. Chapter 11, chapter 12. See ya.